Good morning, students. I hope you are doing well in your studies and managing well through this coronavirus pandemic. Now, this is one of the topics from lecture come demonstration, that is LCD series. And today I will be talking about electrolyte analysis by ion selective electrode and the arterial blood gas analyzer. According to the MCI curriculum, the competency address. Let's look at the biomedical importance of these electrochemical sensors in general. Now, these sensors are well suited to measure blood gases like oxygen, carbon dioxide, electrolytes, and metabolites in autoanalyzers and point of care analyzers. They are easy to use, has low maintenance, and has ability to measure clinically important analytes in undiluted blood. Further, these electrochemical detection has been applied successfully for detecting toxic poisons in blood samples of patients and novel ultra-sensitive immunoassay schemes. Potentiometry is widely used clinically for the measurement of pH, partial pressure of carbon dioxide, and electrolytes like sodium, potassium, calcium, chloride, magnesium, lithium. Before we move forward, let's understand its basic concepts. Potentiometry is the measurement of an electrical potential difference between two electrodes, half cells, in an electrochemical cell when the current is zero. Now, this is a schematic diagram of an ion selective membrane electrode based potentiometer cell. Now, such a cell consists of two metallic electrodes that are connected by an electrolyte solution. This is also known as the ion conductor. An electrode or half cell consists of a single metallic conductor that is in contact with an electrolyte solution. The ion conductors can be composed of one or more phases that are either in direct contact with each other or separated by membranes permeable only to specific cations or anions. One of the electrolyte solution is the unknown or test solution. This solution may be replaced by an appropriate reference solution for calibration purposes. Now, by convention, the left electrode is the reference electrode and the right electrode is the measuring electrode. The electromotive force is defined as the maximum difference in potential between the two electrodes obtained when the cell current is zero, which is measured using a potentiometer. Remember, this cell current should be zero. Now, the zero current is achieved by incorporating a high resistance within the voltmeter. Within any one conductive phase, the potential is constant as long as the current flow is zero. However, potential difference arise between two different phases in contrast with each other. Now, the overall potential difference of an electrochemical cell is a sum of all the potential gradients that exist between different phases of the cell. The potential of a single electrode with respect to the surrounding electrolyte and the absolute magnitude of the individual potential gradients between the phases are unknown and cannot be measured. However, we can measure only the potential difference between two electrodes. Generally, it is possible to devise a cell in such a manner that all the potential gradients except one can be kept constant, and this unknown potential that can be related to the activity or concentration of a specific ion of interest, for example hydrogen or sodium. There are many different types of electrodes that are used for potentiometric applications. Example, redox electrodes, ion selective membrane electrode, which are of different type depending on the type of membrane what they are containing. For example, glass type ion selective electrodes, polymer membrane based ion selective electrodes, PCO2 electrodes. Now here we will be studying only the ISC in details. Ion selective electrodes. So let's look at the ion selective electrodes. The ion selective membrane is at the heart of an ISC, as it will control the selectivity of the electrode. Now these special membranes selectively interacts with the single ionic species and generate membrane potential for the anion or cation of interest. As you can see in this diagram, so one of the molecules of interest will pass through the electrode and will generate electrode potentials. Now the ion selective membranes are typically composed of glass, crystalline or polymeric material. Now the chemical composition of the membrane is designed to achieve an optimal selectivity towards the ion of interest. Now the potential produced at the membrane sample solution interface is proportional to the logarithmic of the ion activity or concentration of the ion in question, as you can see from this graph. So glass electrode and polymer membrane electrode are two types of ISC that are commonly used in clinical chemistry applications. The glass pH electrode is the most common example of an ISC based on use of glass membrane that preferentially binds hydrogen ion. Now typical pH electrode system is shown here in this diagram. Now there are two reference electrodes here, one saturated calomel electrode outside of membrane, one silver chloride with silver chloride layer inside membrane, and pH sensing element. On the picture on the left, there is a glass electrode indicator and saturated calomel electrode reference electrode immersed in a solution of unknown pH. And the pH on the right shows combination probe consisting of both an indicator glass electrode and silver cathode reference. Now let's look at the composition and structure of glass membranes. Now these glass electrode membranes are formulated from melts of silicon and or aluminum oxide mixed with alkali cations. By varying the glass composition, electrodes with selectivity for different ions have been demonstrated. However, glass electrodes for only sodium and hydrogen ions are used in clinical chemistry. Now, hygroscopic substances are substances which tends to absorb moisture from the air. Now, let's look at the hygroscopicity of glass membrane. Now, the surface of glass membrane must be hydrated before it can function as a pH electrode. Non-hygroscopic glasses shows no pH function. Even hygroscopic glasses lose their pH sensitivity after dehydration by storage over a desiccant. Now the effect is reversible. However, and the response of glass electrode can be restored by soaking it in water. Now in this slide we will see that the hydration of a pH sensitive glass membrane involves an ion exchange reaction between the singly charged cations in the interstices of the glass lattice and protons from the solution. Now the equilibrium constant for this process is so large that the surface of the hydrated glass membrane ordinarily consists entirely of the salicylic acid groups. As you can see, the sodium from the glass will go into the solution. So the hydrogen ion moves from the solution and exchange for sodium ions in the glass. Now pH is determined by formation of boundary potential across glass membrane. Let's see how this happens. So whenever there is a charge imbalance across any material, there is an electrical potential across the material. Now the concentration of protons inside the membrane is constant, and the concentration outside is determined by the concentration or activity of the proton in the analyte solution. Now this concentration difference produces the potential difference that we measure with a pH meter. Now at each membrane solvent interface, a small local potential develops due to the preferential adsorption of hydrogen ion onto the glass surface. And we have already seen the glass membrane is specially designed to give preference to these hydrogen ion. Once these hydrogen ion gets into this glass surface, the charge separation happens, and this leads to development of these potentials across the glass membrane. So pH is determined by formation of this boundary potential across glass membrane. Now let's see how the electrical conduction is happening across the glass membrane. Now to serve as an indicator for cations, a glass membrane must conduct electricity. So conduction within the hydrated gel layer involves the movement of hydrogen ion as per the reaction given below. And sodium ions are the charge carrier in the drier interior of the membrane. Let's review all the cell potential in this situation. So first of all, the potential of the two reference electrodes. These are that will depend on the electrochemical characteristic of their respective redox couples. And then the potential across the glass membrane, which we have just seen, depends on the physiochemical characteristic of the glass and its response to the ionic concentration on both sides of the membrane. So we have the four potentials actually. Number one is, for example, E electrode Ag, AgCl, and SCE are reference electrode potentials that are constant. A third potential is the junction potential EJ across the salt bridge that happens that separates the calomel electrode from the analyte solution. And the fourth and the most important potential is the boundary potential, which varies with the pH of the analyte solution. Now pH is determined by the formation of boundary potential across the glass membrane. Now the boundary potential is determined by the potentials E1 and E2, which appears at the two surfaces of the glass membrane from the reaction. The subscript 1 refers to the interface between the exterior of the glass and the analyte solution, and subscript 2 refers to the interface between the internal solution and the interior of the glass. Now these two reactions cause the two glass surface to be negatively charged with respect to the solution with which they are in contact. Now let's see how the boundary potential is calculated. So the resulting difference in potential between the two glass surfaces, that is the boundary potential, now which is related to the hydrogen activity in each of the solutions by this Nernst like equation. For example, now EB is equal to E1 minus E2 and is equal to 0.0592 log of A1 by A2, where A1 is the activity of the analyte solution and A2 is that of the internal solution. Now for a glass pH electrode, the hydrogen activity and activity of the internal solution is held constant, so that we can measure the outside activity. So here in this equation, if you plug L dash is equal to 0.0592 log A2, so EB will come L1 L dash minus 0.592 pH. So the boundary potential is then a measure of the hydrogen activity of the external solution A1. You don't have to go into all these deep calculations, but just you need to know the concept of how the pH is being calculated. So in the next slide, you will be seeing a small video on glass pH electrode in a little bit more detail.
Many liquids are essential in our daily life. They may include water, beverages, dairy products, chemicals, acids and bases, or pharmaceutical products. The quality of these liquids is determined by their chemical properties. To assess these properties, various principles of measurement are used. One of these principles is pH measurement according to the Potentiometric principle. The principle can be traced back to 1909, when the Danish chemist Søren Sørensen introduced the so-called hydrogen ion exponent pH+, to describe the concentration of hydrogen ions in a solution. This was the basis for the development of the conventional pH scale. In 1889, Walter Nernst formulated the Nernst equation that for the first time related electrical voltage to ion concentration. The Nernst equation derived for pH is the physical basis for pH measurement according to the potentiometric principle. Potentiometric pH measurement is the measurement of a potential difference using so-called glass electrodes or non-glass electrodes. In the case of glass electrodes, the pH-sensitive element is a glass bulb that is fused to the end of a glass tube. The electrode is filled with a neutral potassium chloride solution buffered at pH 7 and contains a silver chloride wire that forms the electrical connection. The reference system is located in the outer glass tube and also consists of a silver chloride wire in a potassium chloride solution. A so-called junction protects the reference system from the medium to be measured without disconnecting the electrical connection between them. The pH value is calculated from the potential difference between the reference system and the measuring system. Let's take a closer look at the pH-sensitive glass bulb to understand how this potential difference is formed. Diluted hydrochloric acid, for example, contains large negatively charged chloride ions and small positively charged hydrogen ions. When the pH sensor is immersed into this acid, the hydrogen ions are able to penetrate the boundary area of the glass membrane, the so-called gel layer. The considerably larger chloride ions remain in the solution. The result is a charge separation. The same process occurs on the inside of the sensor with the neutral solution buffered at pH 7 that has a constant concentration of hydrogen ions. If the hydrogen ion concentration, hence the pH value, on the inside differs from the concentration on the outside, a measurable potential difference forms. If the hydrogen ion concentration on the inside is lower than on the outside, as shown here, the measured solution is acidic with a pH value lower than 7. If the hydrogen ion concentration is identical on both sides, no potential difference forms and the measured solution is neutral with the pH value 7. The measured solution is basic if the hydrogen ion concentration inside the glass bulb is higher than in the measured solution.
Now let's look at the polymer-based Iscs. Now polymer-based Iscs are employed for monitoring pH and for measuring electrolytes including potassium, sodium chloride, calcium, magnesium and carbon dioxide. Now these electrolytes use a polymeric membrane which is composed of polymers such as polyvinyl chloride, a plasticizer and the iron carrier or exchanger. Now the response of these electrodes is highly sensitive. Ionophores or chelating agents that selectively complex ions include crown ethers and the antibiotic valinomycin. Now the important feature of this neutral carrier molecule is its cavity, which has dimensions approximately that of a molecule or ion. Now the electron-rich center of valinomycin efficiently extracts potassium ion due to the similarity between the diameter of potassium and the inner diameter of the valinomycin molecule. Now the outer lipophilic part of the valinomycin molecule allows it to remain in the polymeric membrane. So the potassium is selectively extracted and by the membrane. The valinomycin electrode was one of the first polymer membrane electrode and is routinely used to determine potassium. In the United States alone, nearly 200 million measurements are made annually of blood potassium levels using this electrode. Let's look at some of the advantage of ICEs. Now, measurement with ICs are simple to perform, take very less time, non-destructive, that is same IC can be used many number of times, can be used to measure a wide range of concentrations. Measurements of electrolytes by IC is sensitive to molality and is therefore not affected by the variation in the concentration of proteins or lipids in the sample. Thus, there is no risk of reporting falsely low sodium concentration, pseudo-hyponatremia in case of extremely elevated protein and lipid concentration. Now, this usually happens in the techniques such as flame photometry and other photometric methods requiring sample dilution. In these methods, only the water phase of the sample is diluted, producing results lower than the molality as a function of concentration of proteins and lipid in the sample. So this ICEs avoid this issue. Now let's move on to the to study the blood gas analyzer and its clinical applications. Let's look at the biomedical importance of arterial blood gas analyzer. So arterial blood gas sampling is done to confirm rule out hypoxia, that is the oxygen concentration, carbon dioxide levels, retention, acid base abnormality, carbon monoxide poisoning, nitrate poisoning, to obtain arterial blood for other blood tests such as ammonia level, lactic acid levels, etc. Also, ABG used to manage acid-base disorder occurring in various diseases. There is need to know several biochemical parameters like blood pH, PCO2, electrolytes, lactate, bicarbonate, etc. Now, these parameters are measured by blood gas analyzer. Most analyzer measures pH, PCO2, PO2, and electrolytes by means of electrodes and potentiometer, as we have seen earlier. Now this is the picture of ABG analyzer used in the Central Biochemistry Lab. This is GEM Premier 3000 model. Now let's see some of the precaution we should take care while sampling for arterial blood gas analyzer. Now it is to be done on the hyperonized arterial blood sample, and we should avoid tourniquets because sometimes tourniquets are potential source of methicillin resistant Staphylococcus aureus MRSA and should be avoided. Also, the plunger should not be pulled to withdraw blood because additional pressure increases the risk of hemolysis. Let's see the prerequisites for doing ABG sampling. So this is the Allen test. So the radial artery is the most common site for ABG sampling. One of the risks of this procedure is thrombosis, which could decrease or block perfusion distally. So it is absolute necessity to ensure that the ulnar artery provides good lateral blood flow to the hand. So the Allen test verifies the presence of a patent ulnar artery, so which will provide sufficient blood flow to the hand and keep it perfused in the event the loss of flow from the radial artery is there. Now, some of the complications which may arise during sampling of ABG is thrombosis, hematoma, arterial embolism, infection, and hemorrhage. Here are some of the normal values of the parameters which we measure. So pH 7.35 to 45, PO2 80 to 100, PCO2 35 to 45 millimeter of mercury, saturation of oxygen 95%, bicarbonate level 28 to 28 millimole per liter, base difference, excess or deficit, -3 to +3 millimole per liter. Follow. Make sure that at least 5 minutes of firm pressure is kept over the arterial puncture to prevent hematoma. As you know, this is a high pressure system. Now let's look at the principle behind measurement of some of these parameters. For pH, we have already looked at the glass electrode, which is used for measuring the pH in detail. I've just summarized here. You can go back and see the details in previous slides. For measuring partial pressure of carbon dioxide, again a glass electrode is used, which is placed in a weak bicarbonate buffer that is separated from the blood sample by a membrane permeable to carbon dioxide in the specimen. Now the carbon dioxide diffuses into bicarbonate buffer solution inside the electrode and changes the pH by affecting the hydrogen ion. Now concentration in the following way: carbon dioxide plus water gives H2CO3, which will split into H ion and bicarbonate ion. Now the change in the hydrogen ion concentration in the buffer is then measured in the same way as that of pH. Now the gas permeable membrane of the PCO2 electrode excludes hydrogen ion in the solution, that is in the sample. So the pH of the specimen will not affect the observed pH inside the PCO2 electrode induced by diffusion of carbon dioxide from specimen into electrode. Now let's look at the PO2 electrode. So measurement of PO2 is based on the electrochemical measurement of oxygen that diffuses across a gas permeable membrane into an electrolyte contained in a Clark electrode. Now this electrode comprises a silver anode and a platinum cathode immersed in an electrolyte buffer. Now the buffer solution consists of a KCl and phosphate buffer or buffered KOH in water. Now the electrical potential of the cathode is held constant with respect to that of anode. Now oxygen present in blood sample diffuses across gas permeable membrane into the electrolyte buffer, where it is reduced at platinum cathode in following manner. Oxygen, you can see this reaction. Now the reduction of oxygen at cathode results in the flow of current between cathode and anode. Now the amount of current flow is measured and related to the amount of oxygen in the sample. Now calibration of PO2 and PCO2 electrode is done against gases of known oxygen and carbon dioxide composition, which are in the compressed form and used as primary standards. Now electrolytes like sodium, potassium, calcium, chloride, lithium are usually estimated by ion selective electrodes based measurements. Air pressure. The air pressure is measured continuously by an integrated air pressure sensor. The value of PCO2 and PO2 are dependent on the air pressure. Now this is taken into account when the electrodes are calibrated. Hemoglobin. Hemoglobin is also measured by gas analyzer in order to give percentage saturation. Now there are some calculated parameters. Actual bicarbonate. Now this is important in diagnosis of metabolic acid-base imbalance and is influenced by lung function also. Now it is calculated using Henderson-Hasselbalch equation, which we have studied earlier as well. So pH is equal to pK plus log of bicarbonate divided by alpha PCO2, where alpha is the solubility coefficient of PCO2 and its value for plasma at 37 degrees Celsius, and the complete oxygen saturation of hemoglobin. Now standard bicarbonate, now it is a measure of bicarbonate concentration in plasma at a PCO2 of 40 mm of mercury, a temperature of 37 degrees Celsius, and complete oxygen saturation of hemoglobin. Now the other calculated parameters are base excess. It is defined as the concentration of titrable base present in plasma. Now it is determined by titrating the plasma with strong acid to pH 7.4 at the PCO2 40 mm of mercury at 37 degrees Celsius. Now total total carbon dioxide. So total carbon dioxide is equal to the dissolved and carbon dioxide liberated from bicarbonate present in plasma when blood is drawn anaerobically. Now this method relies on the color changes of an indicator in an bicarbonate buffer following a release of carbon dioxide on acidification of the sample. Buffer base. Now it represents the sum of concentration of all buffers in blood. that is the hemoglobin, bicarbonate, protein, and phosphates. So other calculated parameters are oxygen saturation of hemoglobin. Now it shows the percentage of all possible bonding sites of the hemoglobin which are occupied by oxygen. The saturation is independent of hemoglobin concentration. Now total oxygen concentration. Now it is a sum of physically dissolved and chemically bonded oxygen and is mainly determined by partial pressure of oxygen and oxyhemoglobin. Now alveolar arterial oxygen pressure difference. Now it is defined as the difference of oxygen content between alveolar air and the arterial blood gas Po2. Hematocrit, now it is defined as a percentage of red blood cells to the total blood volume. Now procedure in brief. So after putting the instrument on as per the instruction manual and ensuring its proper working, inject the uncoagulated sample directly into the inlet from the syringe. The blood in the syringe is not coagulated, is ensured by expelling a drop on tissue paper. Now wait for the instrument to process the sample. It just takes a few minutes to get the printout of the result. If printout facility is not available, digital displays are also available which will give you the result. So after the sample analysis is over, instrument should be rinsed, washed before putting off or in between the standby modes between the samples. Now some of the precautions we should take while doing this procedure. So sample should not be in direct contact with the air and the needle should be sealed and bent because otherwise the contamination from the atmosphere may happen. So analysis of the sample should be done at the earliest, at most within 1 hour, and samples should not be clotted. Make sure it's not clotted. These are some of the references you can go through, so which I have used in this presentation. So there is the Manual of Practical Biochemistry for MBBS, Dr. S.K. Gupta, ARIA publication, and Textbook of Clinical Chemistry and Molecular Diagnostic, edited by Carl Z. Burtis. This is a 4th edition, elsewhere publication. I hope you have learned quite a lot today. Please let me know if you have any queries. Please follow the lockdown rules and keep safe. Thanks.